Welcome back. I hope that the material in chapter 13 was pretty easy to process. We're going to get into focusing on gases. Gases actually are where modern chemistry kind of started in a lot of ways. It was work with gases that led to a lot of the understanding we have today of matter. So here we go. Chapter 14, gases. You know that if you've played any sports, the ball has to be inflated to the proper pressure. There was a bit of a scandal, you might recall, in football a couple years ago. Anyway, there are certain ways that gases behave that are very, very different, and that's what we're going to focus on. So, solids have a rigid shape. They don't move around on their own. They have a fixed volume and kind of stay together in a organized fashion. Liquids are not rigid, they move around. They don't have a fixed shape. They can change shape, they take the shape of their container, but they do have a fixed volume. Now, that's at certain temperatures, and we'll talk more about that. Gases are not rigid, they don't have a fixed shape, and they have no fixed volume. They expand to fill whatever container they're put in. They take the shape of whatever container they're put in. A couple other things to add to that. Gases are called fluids as well, even though they're not liquid. Most people think of liquids and fluids as synonymous, but so are gases. Very low density, that's because the particles are spread apart, about 10 times their diameter apart from each other. Very compressible. This is a big deal. And they can exert pressure, as we talked about. They're moving around, kinetic molecular theory, bouncing off of walls. It causes them to exert pressure. And again, that's because they're moving. They diffuse. They move from one place to another. This is a cute little video on gases. The variables that we need to focus on are pressure, and those are measured in thousands, kilopascals. Pressure is capital P. Volume, capital V, we measure in liters. There are other ways to measure it, but we'll typically use liters. Those are more manageable than cubic meters. Temperature, which has to be in Kelvin, has to be in the absolute scale, or our work does not go so well. So we'll talk more about that in great detail. And then N for number of moles, how many particles are present, because the number of particles will change these other three factors. So P, V, N, T, and we'll learn more about the ideal gas law at the end of this chapter. So what's easier to compress, solids or liquids? A lot of people think that liquids can compress, but anybody who's done a belly flop knows that is just not true. Okay, so compressibility is what saves lives with airbags. Inflating those at the right time is a whole nother story, but having the ability to squish the bag, change the momentum of a person's face and body is what saves lives in accidents. Gases are compressed, again, because there's tons of space in between the particles. They're zipping around. I mean, this is just a snapshot, if you will. But, and they do hit each other occasionally, but for the most part, they're just flying around in straight line motion. Okay? And again, it's about 10 times the particle's diameter to the next one. See a lot of these piston things to represent gases and their behavior. Remember, the length of the tail is supposed to tell you something about their speed. This has a single mass of something, and this is twice the mass. So under a greater pressure, more mass for the same area creates greater pressure. If you increase pressure, you decrease volume. That's an inverse relationship. Okay, you can squish gases together. Things that affect gases and how, or the volume, temperature, and all of those affect the gas's pressure. So how much space that those particles can move around in and how hot or cold it is will change the pressure a gas exerts. The amount of gas is something that is also useful to someone trying to inflate a raft. What you're doing with a bicycle pump or a inflation device of some sort, a pump, is you're putting more particles in there. So putting more air particles, more gas particles into the raft makes the pressure increase. And keeping them enclosed is good. The collisions that result are creating that pressure with the walls of the container. Now, not all containers are flexible like this raft, so that's also something to keep in mind. Okay? So more particles, more pressure, because there's more of them striking the walls. If you put too much in, right, so pump, it goes to 100 kilopascals, 200 kilopascals, you can, in some containers, exceed the strength of the container and the particles will escape. They can exert that much pressure. Obviously, it depends on your container. The way that a spray can works is kind of interesting. A lot of people don't know that most aerosol cans are filled with carbon dioxide now. Used to be chlorofluorocarbons, but now it's mostly CO2. And they put it at about twice normal atmospheric pressure. So when you push on the valve, that opens the little space here that allows the higher pressure gas to push on the liquid. And again, this is kind of like a barometer. That higher pressure pushes the liquid. Liquid doesn't compress, but the liquid finds a path out through the tube and out into normal atmospheric pressure. So the blue arrows are the internal pressure. Pushing that button opens it. The higher pressure inside pushes on the liquid, and then it comes out. Okay, remember, liquids don't compress. You can also raise the pressure of a container by making the space smaller, like we talked about. So a smaller space, more compressed, more times the particles are going to strike the wall. And so again, we got these little hand pump things, kind of weird. 100 kPa, which is pretty close to normal atmospheric pressure, which is 101.325. 100 kPa inside, outside, it's going to stay level. Push down with a greater pressure, that's going to create a smaller space to equalize the pressure. So if you have the volume, cut it in half, you double the pressure. That's an inverse relationship. Temperature will also cause an increase in pressure. Again, temperature is directly related to kinetic energy. The faster they're moving, the faster they hit, the harder they hit, more energy, more pressure. So we have to do the temperature in Kelvin. 300 Kelvin is about 27 degrees Celsius. That's pretty warm, but it's a nice round number. Okay, double the temperature Kelvin to 600, and you'll double the pressure. And then if you keep going, you might break your container. Okay, so again, doubling the temperature, 300 to 600, doubled the pressure, 100 to 200. That's a direct relationship. They do the same thing. And that's it for section 1. Hope you're well. Till next time.